right, today we're going to talk about dot product and vector applications. So this is a continuation of the notes. The velocity of a moving object is a vector because velocity has both magnitude and direction. The magnitude of velocity, the velocity vector, is its speed. Okay, so let's do some examples here. Find the component form of the velocity of an airplane flying at a bearing of 65 degrees at 500 miles per hour. Okay, so they're giving this to us in bearing language. Yeah, I hear the groaning from the back. So we measure bearings from the north. So here's the north, and 65 degrees is going to be maybe roughly about here, where this is 65 degrees. But if I want the component form of this vector, I need the horizontal distance and the vertical distance here, which requires a different angle. So the angle we're going to need is 65 minus 90, so we're going to make theta equal to 25 here, because that's the angle we need, because we know from trig that this distance here is going to be the x component, which would be the magnitude, which is 500 miles per hour. So this would be the magnitude of the velocity vector, and this would be the angle. So in component form, this would be equal to 500, which is the magnitude, times the cosine of 25 degrees, because we always use the angle with the horizontal to help us figure out what component form is. All right, and then this is going to be 500 times the sine of 25 degrees. And if you wanted to know what the distance was, or the values of this based on, cosine and sine, the approximate values, this would be 453.15, comma, and then we would go 500 times the sine of 25 degrees, and we get 211.31. And that would be the velocity vector approximate form. Okay, so that's easy enough to do. So the thing is if you're given it a flight path in bearing mode, you have to convert this and find the angle measure with the horizontal in order to come up with the component form of the vector. All right, so let's do another one. All right, so these are great problems because when airplanes are flying, they have things that work on them, such as wind. And so I like to do these problems because they're real life and they're fun to do. So let's think about this one. An airplane is flying at a bearing of 340 degrees at 325 miles per hour. So they've given us the magnitude of the velocity of the airplane, and they've given us its bearing. The wind is blowing at a bearing of 320 degrees at 40 miles per hour. So now we have the magnitude of the wind and its bearing. Draw a picture of the airplane, wind, and resultant vectors. Try to draw to scale. Well, when you draw it to scale, that means we just want the airplane vector to be bigger than the wind vector. All right, so let's draw that. Bearing is measured from the north, so here's my north. I'm going to make it lower because I got to have an airplane vector above it. The wind vector above it. Here we go. So here's my north. And 340 is almost all the way around, except we're 20 short. So I'm going to say that this is my wind vector from here. And so this measured angle is 340 degrees, which means this measured angle is 20. But the angle I need to find the component form of the airplane is not this angle or this angle. I need to find this angle because that's the measurement with the horizontal. And so theta in this case is going to be 90 plus 20, which is 110. So we know the airplane direction angle now. All right, so the rest of the problem says wind is blowing at a bearing of 320 degrees at 40 miles an hour. So what we're going to do is we're going to add the airplane vector, velocity vector, with the wind velocity vector and see what the resultant is. So what happens when we add two vectors together? Well, I could put them both in standard position, but that's a little bit more difficult to add or see what's going on. So what I like to do is I like to put them on, get my colored pencil here, together as they will be working together. So for example, I'm going to create my own new XY plane at the tip of the airplane vector, because that's where I'm going to put the tail of the wind vector so I can see how they are working together when I add them. Okay, so I know the wind is blowing at a bearing of 320 degrees. So I'm going to draw the wind vector. Here we go. This is the north for the wind vector. So it's going to be 320, which is 40 degrees short of perpendicular. So here we go. I'm going to make this 40, and I'm going to make it smaller, right? Because we're trying to draw it reasonably to scale. And then this is 40 degrees. And we know that this angle here was the 320 degrees, but that's not the angle I need for this wind vector, is it? Why? No, it isn't. I need this angle here. Well, that angle is going to be 90 plus 40, which is, what do I hear in the background? Oh, I heard somebody say 130, and you would be right. So this angle here, theta, is 130. I needed a color I could see better. That's 130 degrees. So now I have the direction angle for the wind. But what is the resultant vector out of all of these? I'm trying to find another color. The resultant vector is when I go from the tail of the airplane vector and I go to the tip of the wind vector. Now these are going to be pretty tight here, so there is the resultant vector. So what is the wind doing? The wind is pushing the airplane a little bit off from its trajectory, which makes sense because they're working together. Okay, so let's see if we can answer some questions now. This first question says, find the component form of the velocity of the airplane. Okay, so I'm going to say the velocity of the airplane, and put a little subscript here so we know that it's the airplane, is equal to, well, its component form is going to be its magnitude. Well, the magnitude of the airplane's velocity was 325 times the cosine of its direction angle, which was 110, and 325 times the sine of its direction angle, which was 110. And let's put that in the calculator here. We can say 325 times the cosine of 110, and we have to be in degree mode here, and then 325 times the cosine of, the sine of 110. And so does everybody see that is, let's put it here. The approximate value is negative 111.16, comma, 305.40. There you go. All right. Now, these are the approximate answers. Now, when I'm going to find the angle for this resultant and the component form of the resultant, I'm going to use the exact values, which means I'm going to be using the ones that I have up here. All right, so let's find the component form of the velocity of the wind. Okay, so the velocity of the wind is going to be the magnitude of the wind, which they said in this problem was 40 miles per hour. So it's going to be 40 times the cosine of its direction angle, which is 130, comma, 40 times the sine of its direction angle, which was 130. So cosine sine. All right, and let's put that in here. So that's going to be 40 times the cosine of 130, 40 times the sine of 130, and we get negative 25.71, 30.64. All right, so let's see if that makes any sense. Does it look like I probably went over, not as much as I went up for the wind? Yes. What about for the airplane? Looks like I went over negative 111 and up 305 for the, for the wind, or for the airplane. So those makes reasonable sense. Okay, so now find the component form for the velocity of the resultant. So I'm going to put the velocity of the resultant, and what is that going to be? That's going to be the velocity of the airplane plus the velocity of the wind added together. Okay, and so that's going to be 325 cosine of 110 plus, because you just add the x components together and then you add the y components together. Cosine of 130, 325 sine of 110 plus 40 times, I'm running out of space here, story of my life, sine of 130. Just barely made it. Okay, and now we're going to do that on the calculator. Now, I'm going to do a really quick lesson on vectors here, okay, on graphing vectors. Believe it or not graphing, but adding and subtracting vectors on the calculator. Believe it or not, you can write a vector on the calculator by using the curly braces here, which is above the parentheses, and you use the second button, and there's my curly brace, and then my first component is going to be 325 cosine of 110, comma, which is above the 7, 325 sine of 110, and then I'm going to close the curly brace, second curly brace, and so there it is, there's my vector, and then I can do the second one here, second curly brace, 40 cosine of 130, comma, 40 times the sine of 130, close second curly brace, and there's my second vector. And believe it or not, I can take the first vector and add it to the second vector, and we get a resultant. And see if that makes sense. Does that look like negative 111 plus negative 25 would be this number? And the answer is yes. And 305 plus 30 would be 336 approximately. So yeah, it works. It's amazing stuff, these calculators these days, right? So what's my resultant vector? Negative 136.86 or 89, roughly, if I'm rounding to the nearest hundredth, comma, 336.04. Okay. Now, I need to find the magnitude of this vector because I'm asked next for the ground speed, which is the magnitude of the resultant, which is equal to the square root of the components here. Okay, so that's going to be the square root of, now, oftentimes, we're going to go second square root. I'm going to hop up here and see if I can get some of these numbers. Nope, it's not letting me get them. All right. Well, clear. Let's do this. I'm going to save as alpha A the 325 times the cosine of 110 plus 40 times the cosine of 130. And I'm going to store that, stow alpha A. And then I'm going to store the component for the resultant. 325 times the sine of 110 plus 40 times the sine of 130. Close this here. And I'm going to store that, stow alpha b. Oops, I've made it an E. I want an alpha b. There it is. So I've got the x component stored in A, the y component stored in B. And then I can say this is big A squared plus B squared, right? Where A is equal to the resultant component part of X, and B is equal to the resultant component part in the Y direction. Okay, so let's do that on the calculator. And we can show our numbers here, but we've got the exact numbers in the calculator. So this would be negative 136.89 roughly squared plus 336.04 quantity squared. So I'm going to show this rounded answer, but in the calculator I'm going to put the exact. So we're going to go second square root of, now I can go alpha A squared plus alpha B squared, which is nice. And then we get 362.85. Okay. So that's the magnitude, and this is going to be miles per hour. And so the plane's original miles per hour was given as 325 miles per hour. So what did the wind do? Did the wind help out? Well, sure enough, the wind helped out, and now it's at 362.85 miles per hour. But we're not done yet because we have to find the direction. Okay, well, the direction is going to be the angle the resultant has with the horizontal. So let's use the red. The direction is going to be this angle here that the resultant has with the horizontal. So I need to find alpha because the red angle, or the red vector, is in quadrant 2. Okay, so how do I find alpha? Well, alpha, yeah, I heard from the back, is inverse tangent of the positive A component and B component divided, right? So it's going to be B over A. Now, B is a negative number, isn't it? Because, I'm sorry, A is a negative number. So this has to be the opposite of A because alpha is a positive first quadrant reference angle. So we have to make sure we take into account that we know that our A here is a negative number. So we're going to go second inverse tangent of alpha B divided by negative alpha A. Now, why again am I making it a negative A? Well, because our A value, the x component part of the resultant is negative, and I have to have it positive. There we go. So alpha is approximately 67.84 degrees, which makes my direction angle, I'm making a mess on my paper here. My direction angle is going to be 180 minus alpha, so 180 minus my answer, which is 112.16 degrees. So that is the direction and the magnitude of the result of the wind working on the airplane, which is a very cool application. All right, let's do another one. All right, so in this problem, I have an airplane flying at a bearing of 170 miles per hour. At a bearing of 170 degrees at 460 miles per hour. The wind is blowing at a bearing of 200 degrees at 80 miles per hour. Draw and label a picture of the airplane, wind, and resultant vectors, and try to draw to scale. Okay, so I have, this one is very similar to the one I just did. So what I'd love for you to do is pause the video for a few minutes and you work it and then compare your answer to what I get. Okay. All right, you're back. So here we go. I hope that you drew the airplane vector first with a bearing measured from the north, of 170, which means it's almost 180. So it's going to be down here. There's my airplane vector. So this right here is 170 degrees. And we know then this angle is 10. But that's not what I need because I need it measured from the horizontal. For the airplane, I need its direction angle to be this angle here. So theta would be not 270, but 10 plus 270, which is 280 degrees. Okay, so right now I'm ready to draw the component form for the velocity of the airplane. So here we go. The velocity of the airplane is going to equal its magnitude, which is 460 miles per hour, times the cosine of its direction angle, which is 280 degrees, and 460 times the sine of 280 degrees. And if we put that on the calculator, we can say 460. Actually, I'm going to put this in vector form, right? So second curly brace, 460. 460 times the cosine of 280, comma, 460 times the sine of 280, close second curly braces. There we go, and we get 79.88 roughly, comma, and then negative 453.01. So let's use our number sense. Does that look reasonable that I went over just a little bit and way down on the y? And the answer is yes. Okay, great. So now we're going to do the wind. All right, so let's see. The wind has a bearing of 200. So what do I do with the wind? Well, what I do is I put a new set of XY axes on the tip of the airplane because the wind is going to work on the airplane and we're going to add them together to get the resultant. Okay, and so the bearing is measured from the north and 200 is 20 degrees past 180. So it's going to be over here and it's going to have a little bit more of an angle here. So this in here will be 20 degrees. I know it's hard to see, but that's 20. And then this angle from here to here is 180, but that's not the angle I want, is it? I know it isn't. It's not the angle I want. I want this angle for the airplane. I want this angle. Right? So theta equals, well, it's not 270. It's 20 short of 270, which is 250. Okay, so now I know the angle for the direction angle for the wind. So let's write the velocity vector for the wind. So what do we get? We get, well, it's going to be the wind's magnitude, which is 80, times the cosine of its direction angle, which is 250. 80 sine, whoops, I forgot my zero. Sine of 250. And we're going to put that in the calculator and see what we get. There, the light comes back on. All right, second curly brace. 80 times the cosine of 250, comma, 80 times the sine of 250, close second curly brace. And I press enter, and there's our component form for the wind, which is negative 27.36, comma, negative 75.18. So that's velocity of the wind. All right, so now I want the component form of the velocity of the resultant, which is going to be nothing more than adding these two vectors together. Oops. I wanted to show that I was adding those two vectors together. So this would be the velocity of the airplane plus the velocity of the wind. And when we add those together, I'll try to write smaller this time. This is going to be 460 times the cosine of 280. Oops, plus 80 times the cosine of 250. And then it would be 460 times the sine of 280 plus 80 times the sine of 250. Now, since I already have these two vectors in my calculator, I'm just going to come up and grab this one and add it to the answer. Maybe it'll let me grab it. Let's see if that makes sense. 79 minus 27 looks like it could be 52, and negative 453 minus makes it even more negative. So I agree with those numbers. So that's negative 50, oh, sorry, positive 52. Positive 52.52, comma, negative 528.19. All right, but the one thing I haven't drawn here is my resultant. So here it goes. So how do we draw a resultant vector? Well, we connect the tail of the first vector we added to the tip of the last vector we added. So here it is. Here's my resultant. Red for resultant. You see the nice color alliteration. So this is a resultant. Okay, and I need its angle of rotation, right? Its direction angle is going to be this angle here. Now, if we look at our component form of it, it's got a positive, even though it looks like I have a negative here, it's positive, right? Yes. Yes, Mrs. Muller, it's positive. Yep, you're right. So this is a positive x component and a negative y component, which means I added a fourth quadrant angle to a third quadrant reference angle, right? I'm sorry, fourth plus third gave me, I'm still in the fourth quadrant here. So I need to find alpha. So basically, my resultant kind of looks like this, and I'm trying to find this alpha. Well, how do we find alpha? Well, remember, how do I do this? I store things in A and B. Okay, so I want to store, so we can go stow. No, I don't want to store the answer. I want to do 460 times the cosine of 280 plus 80 times the cosine of 250. And I want to store that in alpha A. There we go. So that's now in A. Now I'm going to store the other one in alpha B. Now I can grab this, bring it down, and I can change these cosines to sines. I don't know if that's any faster than typing it out, but I'll let you guys be the judge of that. And then we're going to store it into alpha B. All right, so those, I've got A and B are my components. So I'm going to do the inverse tangent now of the B now is negative. The B is negative, so I'm going to make this negative B over A because alpha has to be a positive angle. So we're going to go second inverse tangent of negative alpha B divided by alpha A. And we get alpha equals 84.32 degrees. Now that looks really reasonable based on our picture up here, so I feel good about that. But what is theta? Well, theta is, since this is in the fourth quadrant, is going to be 360 minus our answer there, which is 275. Whoops. I've got writing dyslexia today, so 68 degrees. Okay, so now I've got to find the magnitude, right? So because we've got the direction of our resultant, direction. And the ground speed is going to be the magnitude of the resultant. Now, where did I store these component parts? Well, I stored them in A and B. So this is going to be A squared plus B squared. And remember, I said A was 52, oops, I can recover, 52.52 quantity squared plus negative 528.19 quantity squared. All right, let's do that. How do we do that? Second square root, alpha A squared plus alpha B squared equals 530.79 miles per hour. That's the magnitude of the resultant. So the wind gave us some more miles per hour and changed the direction or angle of our flight. Okay, here we go. Let's do the next one. All right. This next one. An airplane is traveling at a speed of 500 miles per hour on a bearing of 330 degrees at a fixed altitude with a negligible wind velocity. As the plane reaches a certain point, it encounters a wind velocity of 70 miles per hour in the direction of 45 degrees east of north. What are the resultant speed? What is the resultant speed and the direction of the plane? So, all right, so how do we do this? Let's draw our picture because I'm a visual person. We're the airplane's traveling at 500 miles per hour on a bearing of 330, which is 60 degrees away from north. I want to say as the crow flies, but I don't know. Okay, here we go. This is 330 degrees. But I'm going to ask you the question, is that the angle we want to be able to get it into component form? Oh, and I hear in unison. I'm so happy to hear that the answer is no, Mrs. Muller, we can't. We can't have that angle. We need the angle measured from the horizontal. That's right. This is the direction angle. So how do we get the direction angle? Well, we say 90 plus 60, right? Because we know this is 60 and this is a 90-degree angle. So we get theta equals 150 degrees. Great. Well, then we encounter a wind that has a velocity of 70 miles per hour in the direction of east, 45 degrees east of north, because remember, that's how we read that. So I'm going to draw, like I always do, the XY plane at the tip of the airplane vector because, we're going to add them together. And at a bearing of 45 degrees east of north. Well, 45 is right in the middle. I'm going to draw it shorter, right, because it's a wind. Okay, so this is the velocity of the airplane. This is the velocity of the wind. And the resultant, obviously, would be if I connected the tail to the tip. My chair is squeaking. There we go. But I need the angle for the velocity vector for the wind, right? Well, that's easy enough, I think. Does everybody see that theta there is, this theta here is 45 degrees? Good. All right, so let's write the velocity vector for the airplane. Well, we know its magnitude is 500, so this would be 500 times the cosine of its direction angle, which is 150. And then 500 times the cosine of its direction angle, which is 150. The velocity of the wind, so you're going to get really good at these problems, is, well, they tell us the magnitude is 70 of the wind, so this will be 70 times the cosine of its direction angle, which is 45 degrees, times 70 times the sine of 45 degrees, which is its direction angle, right? And then the resultant would be me just adding these two together. The velocity of the resultant is going to be 500 times the cosine of 150 plus 70 cosine of 45 degrees, 500 sine of 150 plus 70 times the sine of 45 degrees. Now, all of these angles are ones that we know from the unit circle. So I could see something like this being on a non-calculator section. But, you know, for what we're doing today, 3:30. Oh gosh, I have to go back in time. Are we rolling back the tape? I caught myself. This is not 60, is it? 3:30. This is 30. This angle's 30. Oh my heavens. You guys probably screaming at the video, right? This is Muller, that's 30. It is 30. So 90 plus 30 is 120. Holy smokes. It's early, right? In my defense. Modeling humanity every moment of every day. So that's 120. Holy Toledo. Yeah, well, we figured that out. Thank goodness. So this is, sorry, 120. 120. Well, you guys knew enough to fix it. And I don't have the time to go back and redo all of this video, so we're just going to have to bear with me. Well, the good news is that I had something haunting me, right? Saying, oh, and I know it was Mr. Turner there on the right-hand side of the room. But Mrs. Muller, that is what? Not 150, it's 120. And you'd be absolutely right. Okay, let's triple check that, right? Because 360 minus, see, I was thinking about the 60 and the 360. So 360 minus 330 is 30 degrees. So that's 30. As much as I try to be perfect, you know, it never works out for me. So I just got to get used to that. Anyway, we just have to love Mrs. Muller the way she is. All right, so what I'm going to do is I'm going to go right ahead and store the component parts here. So I'm going to go 500 cosine of 120, thankfully, now that we got it right before we stuck in the calculator, 70 cosine of 45 degrees, stow alpha A. So there's the component part for the resultant in the x direction. And now let's do the y direction. That'll be 500 sine of 120 plus 70 sine of 45. It's going to be a long time before I stop thinking about that. Mistake. I always like to be perfect in these things, but it's not going to happen. All right, negative 200.50 and then 482.51. So let's see if that makes sense with our picture. I went over 200 and up 482. That looks reasonable. All right, but that's the resultant vector. I want its magnitude. And this is a second quadrant angle because the x component is negative. Right? So we're going to go, oh, I forgot to store this one in B. There it is. I stored it in B now. Okay, so now we're going to do the square root of a squared plus b squared. Second square root, second square root, alpha a squared plus alpha b, You know, you just get off track and then I just got to let it go. Okay. So that's going to be negative 200.50 squared plus 482.51 quantity squared. And I use the exact value, so the magnitude of our resultant, using the proper angle of 120 degrees, is 522.51 miles per hour. Okay. Now I got to find the angle of the resultant. I got to find this angle here, because that's its direction angle. I'm sorry, you should see that, right? The red direction angle here. Got to find that. How do we do that? Well, we're going to do alpha as equal to the inverse tangent of, now which component is negative? Well, it's the A. So we're going to go inverse tangent of B over negative A. Here we go. Second inverse tangent of alpha B divided by negative alpha A. Close the parentheses, and there we go. We get 67.44 roughly degrees. Now that is this angle. We need this angle. So it's a second quadrant angle, so we'll go 180 minus that. And we get 112. So the theta, or our direction angle, is 112.56 degrees. Now, if I wanted to have the answer in bearings, that would be a little bit more interesting to get. And I've asked for that question sometimes on tests. So what would you do? We know that this angle here is 112.56 degrees. You know, bearing angle. Well, that would be, what is 90 minus 112, right? Because if I get rid of this angle here, it'll give me this angle here, which will give me the bearing angle. So I'd go 360 minus, I'm sorry, clear that again. Second answer minus 90 gives me 22.56. So I go 360 minus second answer, and I get the bearing angle would be 337.44 degrees if I asked you for it in bearing language. So that just takes one other computation. All right, moving right along. Hopefully we'll get through number 5 with a better angle situation. All right, let's see, number 5. A plane is leaving San Francisco and flying due east. There is a 65 mile per hour wind with a bearing of 60 degrees. Find the compass bearing the pilot should follow to determine what the ground speed will be, assuming the speed with no wind is 450 miles per hour. Okay, so this is an interesting question because they're telling you what the pilot is flying. So the pilot is flying at a certain, he's flying due east. So due east means this. I'm going due east. Okay. There's a 65 mile an hour wind with a bearing of 60 degrees that pushes him there. Okay. So this is the resultant, basically. They're telling me the resultant, and I need to have what the pilot is flying plus whatever this wind is to get me here, if that makes any sense. So I know that this is a bearing of 60. Let's try that again. Let's think about that. Now I'm going to add this backwards, I think, which is going to sound a little bit weird. So what I'm going to do is I'm going to put the wind vector in standard position here, because then the plane's going to have to fly at a certain magnitude and speed to get there. So I'm going to put the wind here. Here's the wind. Because it doesn't matter if I add the wind to the airplane or the airplane to the wind, right? Because we can do that with vectors. That's commutative property. So the wind is traveling at a bearing of 60 degrees, so which means this angle here is 60. I'm triple checking that in my head. Yes, that's 60, which means this is 30 degrees. And then I have to add the airplane vector to get here. So I'm sorry, it took my brain a minute to think about what we're doing. So this is the airplane vector. This is V of A, and this is V of wind. So I'm going to add the wind to the airplane vector to get the resultant. But they're telling me what the resultant is, right? They're telling me that the resultant is we don't know. what the resultant speed is. So I'm going to go the magnitude of the resultant times the cosine of, well, what is the angle of the resultant? Well, it's 0. Magnitude of the resultant times the sine of 0, because we're going due east and that angle is 0. All right, so if I were to write this out, it would be the magnitude of r times the cosine of 0, which is 1, right? And then this would just be 0 because the sine of 0 is 0. So I got the resultant vector. Now I need the velocity of the wind. Well, they told us it was flying at a bearing of 60, and it gave us our magnitude. So we know that that's 65 times the cosine of 30 degrees, and then 65 times the sine of 30 degrees. We know that one. And I need the velocity of the airplane. I should put this as the velocity of the resultant. Okay, the airplane. Well, we know that it's, with no wind, its magnitude is 450. So we know it's 450 times the cosine of theta, because we don't know what its theta is. And then 450 times the sine of its theta, and we don't know what its theta is. Okay, well, but what do I know? I know that this x plus this x has to equal the magnitude, and this y plus this y has to equal 0. So we're going to solve for the y component first. So what does that mean? 450 times the sine of theta plus 65 times the sine of 30 equals 0. Okay, so I'm going to move this over so we get 450 times the sine of theta, because we've got to get the sine of theta all by itself, equals negative 65 sine of 30. Sine of theta equals negative 65 sine of 30 degrees divided by 450. Okay, and we know that the sine of 30, believe it or not, is 1/2. So this is negative 65 over 2 divided by 450, which equals negative 65 over 900, I believe. So how do we find alpha? Sine is negative, right? So that's going to be in either quadrant 1 or 4, but I suspect it's 4 based on our picture. So we're going to find alpha, right? So we find alpha is inverse sine of the positive 65 over 900. So inverse sine of 65 divided by 900, and alpha is 4.14 degrees, which means theta is equal to 360 minus that, which is 355.86 degrees roughly. Okay, so that's this theta here. Now, why did I use inverse sine instead of inverse tangent? Because I'm, solving the sine here. All right, so that's what the theta is for the wind. Okay, so if I know the theta for the wind, for the airplane now, for the airplane, can I find its components for the velocity of the airplane? The answer is yes. So this is now going to be 450 times the cosine of 355.86. 450 times the sine of 355.86 degrees. Okay, so I'm going to stow an alpha c now. Okay, so I'm going to store that. So the velocity of the airplane is going to be 450 times the cosine of alpha c which is 448.82. And I'm going to store that, stow alpha A, because that's the x component. And then I'm going to do 450 times the sine of alpha C, because that's where I put theta here. And that's negative 32.50. And that makes sense to me because we said we were, going over blah, 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 448 and then down 32. That makes sense. Okay, so I'm going to store this in alpha B. There it is, alpha B. And then the magnitude of the airplane, we already know that's 450, so we don't need that. But what I'm trying to find is, it says find the compass. Oh, yes, I do need that. I do need that. Because I'm going to add this one, because that's the airplane, to the wind to get the okay, yeah, that's what I need to do. So I need to find the resultant. Sorry. The velocity of the resultant is going to be v of A plus the velocity of the wind. Okay, so when we add the velocity of the wind up here, using, cosine of C here and C, because we saved those in C. Okay, so I'm going to add 450 times the cosine of alpha C plus 65 times the cosine of 30 degrees. And that's going to give me 505.12. And then I'm going to copy this and change those to sines. Ooh, wow. That's basically 0, isn't it? Which is what we would expect, right? Because we know that this is going to be 0. Because think about how many zeros that is in front of this number. That's 10. So this is essentially 0. So the magnitude of the resultant, is 505.12 miles per hour. And we know its direction is due east. All right, sorry about for the slight mix-up here in the beginning, because I had to rethink how I was going to do this. So what I did was, you can add the wind first to and then you can do the wind vector and then add the airplane vector to it, and then you find an equation for the resultant, because they told us due east, and then the wind's magnitude and its direction, so you can find that vector, and we know that the velocity of the airplane has to be its magnitude times its angle, which you don't know, but we can solve for the angle by adding these two y components together, setting it equal to 0. And so then we can solve for theta, which we have solved for theta, got 355.86. And so now I know this theta, so I can add these two vectors together to get the velocity vector, which we did for the resultant down here. And then we can find its magnitude. So it's pretty cool. I like that problem. That's a nice one. Made my head even hurt this morning. All right, here we go. Sometimes we have problems where we use forces. Okay, and Newton is the unit of force. So if a 50 Newton force is acting on a pink ball at a 20-degree angle from its positive x-axis, write the force in component form. Okay, so I have 50 Newton force acting on a pink ball at a 20-degree angle from the positive x-axis. Okay, so here we go. Here's my positive x-axis, and this is bigger than 20 maybe, but that's 20 degrees, right? And my magnitude of my force is 50 newtons. So write the force in component form. So I would say the force is equal to the magnitude, which is 50, times the cosine of its direction, which is 20 degrees, times 50 times the cosine of 20 degrees. And it's as simple as that. So it'll be 50 times the cosine of 20. Now, I remember we can do curly braces, right, to do our vectors. So it's 50 times the cosine of 20, comma, 50 times the sine of 20, close second curly brace, boom. And so the force vector is going to be, what is that? 46.98, 17.10. And this is the forces component in the x direction and the force component in the y direction. Okay, that was an easy one. We needed an easy one after that last one. Okay, here we go. One force of 100 newtons acts on an object 10 degrees east of north. Another force acts on the object 50 degrees east of north. Find the magnitude of result and the direction of the resultant. So all we have to do is add these two forces together because they're acting on the same object. But they're giving us and giving it to us in bearing language. So I'm going to draw a really quick picture. Here's north. And 10 degrees east of north means this is 10 degrees. So my angle with the horizontal is 80 degrees. Very nice. So I'm going to call this force 1. Its component form is going to be its magnitude, which they told us was 100 newtons. So it's going to be 100 times the cosine of 80 degrees, and then 100 times the sine of 80 degrees. And force 2 has its bearing is, this is the north, 50 degrees east of north. So this is going to be roughly maybe right about here. So if this is 50 degrees, this here is, let's hear it everybody, 40 degrees. You're right. So this force 2's component form is going to be its magnitude, which is 80. 80 times the cosine of 40 degrees. 80 times the sine of 40 degrees. And what do? We just add them together. So the force resultant, I should put vector language on this, is equal to, well, we just add these two components together. So it would be 100 cosine of 80, oh, my S looks like an 8, cosine of 80 degrees plus 80 times the cosine of 40 degrees, and then 100 times the sine of 80 degrees plus 80 times the sine of 40 degrees. There we go. So let's see. Second curly brace, 100 cosine 80 degrees plus 80 cosine of 40, 40, comma, 100 sine of 80 degrees plus 80 sine of 40 degrees. I got too many 80s going on here. It's driving me crazy here. Okay, so the resultant force vector is 78.64. Whoops, sorry, I should make it 5. 645 and 149.90. But they want the magnitude and the direction. Well, this is the vector, so I need the magnitude of the force vector of the resultant. Okay, so how do I find the magnitude? Well, I'm going to say, clear. 100 times the cosine of 80 plus 80 times the cosine of 40. And I'm going to store that number in alpha A, because that'll be the x component. And then I'm going to do 100 times the sine of 80 plus 80 times the cosine of 40, sine of 40. And I'm going to store that in alpha B. And then to find the magnitude, we're going to do the square root of these component parts squared. So let's do that. We go second square root, alpha A squared plus alpha B squared. So much nicer than typing those numbers in again. Okay, and we get the magnitude of the force is equal to 169.28. And this is going to be in newtons. Now, how do I find its direction angle? Well, this is a first quadrant angle because of both components are positive. So I can just do right ahead. Theta equals the inverse tangent of the y over the x, which is 149.90 over 78.65. And in this case, it's really b over a. So second inverse tangent, second inverse tangent of alpha b divided by alpha a, close parentheses, and we get theta equals 62.32 degrees. So my direction, 62.32 degrees. My force is 169.28 newtons. And if I wanted a bearing angle, what would I do? Well, this angle right here is the 62.32, right? Because that's measured with the horizontal. The bearing angle is going to be 90 minus theta in this case. It's not always that, but it's going to be in this case. So 90 minus second answer, and this would be theta. The bearing angle would be 27.68. And since they gave it to us in this nice bearing language, we could say north 27.68 degrees east, right? All right. I know this is pretty long, but I wanted to get through all of these. Number 8. Two forces, one 35 and the other 50. Okay, so I want you to pause the video for a second, and I want you to work this and then get back with me here in a second and see if you get it right. Okay. Welcome back. Force factor 1 is 35. Now, this says the angle between the forces is 30. So I'm going to put one of the forces in the x direction. So angle is going to be so its angle is going to be 0. Because I could choose where to put these vectors, really. Okay. So 35 times the cosine of 30 degrees. 35 times the sine of 30 degrees. Force 2's vector is going to equal 50 times the cosine of 0. 50 times the sine of 0. And we know this is 0, which is really nice. Okay, so force resultant is going to be equal to force 1 plus force 2. So that's going to be 35 times the cosine of 30 degrees plus 50 times the cosine of 0, which is really just 50. Let me figure that out. Okay, so then this is 35 times the sine of 30 degrees plus the sine, or 50 times this is a 5, sine of 0 degrees. Okay, so on the calculator, we're going to go 35 times the cosine of 30 degrees. I'm sorry, we're going to clear this out. 50 times the cosine of 30 degrees plus 50, because cosine of 0 is 1. So this is going to be 93.30, and I'm going to store that in alpha A. Okay, and then 35 sine of 30 degrees. And the sine of 0 is 0, so this is 0. So this is 17.5. And if I want the magnitude, and I'm going to store in alpha B, the magnitude of this resultant vector is the square root of 93.30 quantity squared plus 17.5 quantity squared, which is second square root alpha A squared plus alpha B squared. And that's going to be 94.93 pounds, because that's also a force measurement. And now I need the angle over the resultant. So what is that going to be? This is a first quadrant angle again, so I can go directly to theta equals inverse tangent of B over A in this case. So second inverse tangent of alpha b divided by alpha a, close parentheses, and theta equals about 10.62 degrees. And we don't have to talk bearings here because the question didn't ask us about bearings, okay? All right, number 9, which happens to be almost the last one. Two forces, one 100 pounds and the other 150 pounds, act on the same object with angles of 20 and 60 respectively. With the positive x-axis, find the direction and the magnitude of the resultant. Again, I ask you to pause the video and see if you can do this one without me. All right, welcome back. 100 cosine of 20. 100 sine of 20 degrees is force 1. Force 2's vector is going to be 150 times the cosine of 60 degrees. 150 plus the sine of 60 degrees. Then we're going to add them together to get the resultant force. Let's do that. We get 100 cosine of 20 degrees plus 150 cosine of 60 degrees. And I'm going to store that in alpha A, right? Because that's my x component of the resultant, which is 168.97. Then let's do that for the y component. We're going to get 100 sine of 20 degrees plus 150 times the sine of 60 degrees. And we get 164.11. I forgot to store that into alpha B. So we're going to store this into alpha B because that's the y component. All right, so the magnitude of our resultant vector is second square root alpha A squared plus alpha B squared, which is 235.54 pounds. And this is also a first quadrant angle here, so I can go directly to theta equals inverse tangent of B over A because they're both positive. So theta equals second inverse tangent of alpha B divided by alpha A, and we get theta is 44.16 degrees. So these are pretty simple, really simple problems. What do? You just add the forces together, the x components and the y components, and get the resultant vector, and then find its magnitude and its direction based on what quadrant it's in. Okay, yay, it's the very last one. Lisa and Gina are pulling Aaron in his little red wagon. I should have a picture for this, but I don't. Gina pulls at 10 degrees east of north with a force of 160 newtons. Lisa pulls at 30 degrees west of north with a force of 190 newtons. What is the magnitude and direction of the result? Now, the only twist on this one is that they give us bearing angles, which we don't need because bearing angles don't help us when we're trying to figure out a component form of forces. So let's draw my north. Here's my north. And 10 degrees east of north is going to be really close here. This is 10. So what is the angle here? Well, this is going to be 80. So Gina direction angle is 80. Lisa's, she's going to pour she's west of north. So Lisa's direction angle, she's west of north. So this is 30 degrees west of north. Her direction angle is this way. So it's going to be 90. 90 plus 30 is 120, right? I'm going to add correctly this time. I'm still smarting about that one back before. Okay, so those are their direction angles. Theta equals 80 and theta equals 120. All right, so force Gina is going to be her magnitude, which is 160, times the cosine of her direction angle, which is 80. 160 times the sine of her direction angle, which was, 80. Force Lisa. Her magnitude is 190. So 190 times the cosine of her direction angle, which is 120. 190 times the sine of 120. And then what are we going to do? We're going to add them up to get the force combined. So I'm just going to put resultant. So let's add them up. And I promise I try to remember to store them this time. So it'll be 160 cosine of 80 plus 190 cosine of 120, stow alpha A, and then we have 160 times the sine of 80 plus 190 times the sine of 120, stow alpha B. Yay, I remembered this time. All right, so what is our resultant force? Our resultant force vector is negative 67.2122, if I round. 322.11. Okay, and this makes sense to me because, I'm sorry, but Lisa's pulling with a much larger force. So, you know, she's pulling it more her direction, which makes sense that this would be a second quadrant angle. I hope that makes sense to everybody. Okay, so how do I find the magnitude? Well, remember I stored these in alpha A and B. We're going to take the second square root of negative 67.22 squared plus 322.11 quantity squared. That's alpha A squared plus alpha B squared, and we get 329.05. This is in newtons. That's the units for this force. That's a lot of newtons. Okay, so now I have to find alpha because this is a second quadrant vector, isn't it? So I got to find alpha and then add, or go 180 minus. So alpha is going to be, which component is negative? Oh, yes, I heard it from the back. The A is negative. So we're going to do inverse tangent of B over negative A to force it to be a positive. So alpha equals second inverse tan of alpha B divided by negative alpha A. And we get 78.2, oops, I can't write. I'm just excited because this video is going to end. And it's been a long one. I'm really sorry. But then what is theta? Theta is going to be 180 minus alpha. So we're going to go 180 minus answer. Oops. And that's 101.79 degrees. So the force is 329.05 newtons, and the angle, the resultant angle is 101.79. But that's not the bearing angle. So let's talk about the bearing because they gave us it in bearing. The bearing angle. Well, I need this angle, don't I? Because that would tell me the bearing. If I know this is 101, I'm going to take the answer and then subtract 90, and that's going to give me, this angle is 11 point, so this angle here is 11.786 degrees, right? So I'm going to go 360 minus second answer, and we get, the bearing angle is going to be 348.21 degrees, which means we're 11.79 degrees west of north, right? So there we go. Ta-da! We've done a lot of force problems. We've done some airplane problems. And I think that's enough for one virtual day. You guys have a blessed day. And thank you for hanging in there and listening. And we're going to make it through all this madness. God bless you.